Okay, this is my demo 9, part 1 for the ALU. So I decided to do the 4 functions that I added. I decided to add a increment by 2, uh, complement of 2, a shift to the right, and then a bitwise XOR. And so I'll just go through each one. I guess I'll start with 4. So what we're going to do is go to our selectors and put in 4. So that will be uh, 0, 0, 1. And then so now we should be in increment by 2. And for our input, we'll go ahead and do 0, 1, 0, 1. And then we should get an output of 7, which we do. So pretty much what that is doing is adding 5 plus 2. So incrementing by 2. So our output is 7. Okay, now I will move on to 2's complement, and that is number 5. So then we'll change the selector to 5, which will be a 4 and a 1. So now we should be in complements of 2. And for this one, I'll do the input 0, 0, 1, 1. And so that's 3 in binary. And in 2's complement, that should give us 1, 1, 0, 1, which it does. And that would be 1. That would be a 1, 5, 13. So that is 2's complement. So I'll move on to 6, which is shift right. So we'll change our selector to 6, which is a 4 and a 2. We'll turn these off real quick. So shift to the right, pretty much all we're doing is shifting one binary to the right. And so when we have the input of 1, we get all zeros. Then if we have 2, we should have the output of 1, and we do. And then if we have 3, we should have the output of shifting 1 to the right, which is 1. And same things. So 1, 1, 1, we get 1, 1. And then for all ones, we get 1, 1, 1, 0. So it's pretty much just shifting one binary number to the right. And then for my last one, I did a bitwise XOR. So we'll turn these off real quick. What's happening with this one is, or for the selector, it's number 7. So, sorry, 1 second. We will go to 7. Which will be 4, 2, and a 1. So now we should be in bitwise XOR. And so with bitwise XOR, in the circuit I built, pretty much what it's doing is splitting them bit by bit and then comparing them with the XOR gates and then putting them back together. So when we have a input of 1, pretty much when they're opposite, we get an output, that output. When they're the same, we get no output. So if we put a 1 right here, we should get a 1 right there, and then another 1, and then if they're the same, it goes back to 0. And so that is working. The last question is discuss why it is useful to have a multifunctional calculator like this as the center of a microprocessor. And just a couple of things I thought of was, one, it performs core computations, so it handles arithmetic, add, subtract, increment, and logic, so like your and or not XOR operations, which most programs rely on constantly. Another reason would be that it supports control flow. So comparisons such as less than, equal to, or 0 allow the CPU to make decisions, which is essential for loops, if statements, and branching. And so yeah, that is my Demo 9 Part 1 ALU.